So today we're going to look at functions, and we're going to do the basics of functions inside of this particular lecture. And so what I want to do is I want to actually first start with the definition of a function. It's going to look very similar to something that you've seen inside of mathematics, hopefully, and it has the exact same meaning. So we say that a function f maps elements of a set x to elements of a set y, and creates a subset of the domain x cross y such that for every x belonging to x, there's exactly one y belonging to y. And this part here, this second part here, okay, is going to end up becoming pretty important for us in terms of determining whether or not something's in fact a function, or what we call a well-defined function. So let's first just give an example, and I'm going to use something called an arrow diagram. And so we're going to have my set x over here. And let's say x is 1, 2, 3, 4. And we'll have y be 1, 2, 3. And 4 and 5. How about that? That's what we'll do. And so we're going to take 1, and we're going to say that 1 maps to 2. So basically, when I take my function x, what x does is it takes 1 to 2. And then it'll have from 2 to 3, from 3 to 1, and then how about from 4 to 3? Okay? And it turns out that this is a function, or a well-defined function. And if we look, first, every x belonging to x, so every x, 1, 2, 3, and 4, is actually mapping to something in y. Okay, something in y. That's the first thing, right? And then it's mapping to exactly one y. So 1 maps only to 2. 2 maps only to 3. 3 maps only to 1. And 4 maps only to 3. Okay? So what we're saying here, it doesn't necessarily mean that, for example, that we might have two elements that map to the same elements in x that map to the same element in y. For example, like 4 and 2 both map to 3. That's fine. That's not a problem. Okay? What we need to make sure, though, is that if 2 maps to 3, then 2 doesn't also map to something else. Like 2 can't map to 4, right? And the reason for this has to do with the idea of a function and the effectiveness of a function. So for a function, we want to be able to take an input and we want to be able to map it onto an output and know that we're going to get one and only one output for that particular input. So another one, if we were looking algebraically, so we'll call this example 2, is we'll take f of x equals 3x minus 1. So we've got f of x equals 3x minus 1, and so any element that I take for x, let's say I let x equal 4, okay, and I plug that in, and what I'm going to get is I'm going to get f of 4 equals 3 times 4 minus 1, which equals 11. All right? There's no other way to get anything else when I plug in 4 other than 11. All right? That's just how this thing is defined algebraically. And you can imagine that for any set of values. Okay? Any set of values here that I plug in for x, I'm going to get one and only one y back. And so hence, this f of x also is a function as well. And so that's our definition of a function. Right? For every x belonging to x, there's exactly one y belonging to y. So the next definition that I need here is this idea of a domain and a codomain. So in our previous example about functions, we had the set x, and that was where we were pulling everything from. Okay, we were pulling everything from the set x, and then we were going to map that in onto, or to map to the set y, and we're going to call that set y the codomain. Okay, so the first thing that we need to get, all right, is that we can choose any domain that we want, and we can choose any codomain that we want. This is just going to be the set of elements that we're going to end up pulling from. So for example, I might actually take my domain, and I might define it as the set Tom, Lisa, Terry, and Jean. So I've got a group of people, Tom, Lisa, Terry, and Jean. And what I want to do is I'm going to say, okay, well, for me to have a function, I'm going to have these 4 people, Tom, Lisa, Terry, and Jean, and they're going to have to map to something. And so what I'm going to do is I'm going to define my codomain as the set of 4-digit strings, all right, with an alphabet of 0 to 10. So we'll have our alphabet be 0 to 10. These are going to be 4-digit strings. So what you can imagine is like that we have a nice set of identifiers. So like, you know, we've got a group of, say, maybe 1,000 people or yeah, a set of 1,000 people. We want to give each one of them an individual and unique identifier. Okay? And so consequently what we're going to do is we're going to say, okay, so I've got 1, 1, 2, 1, 1, 3, 4, 7, 2, 3, 1, 5, and 4, 8, 2, 1. Okay, so each one of those elements, that's my codomain, or these are members of my codomain. Now my codomain is actually quite a lot larger. All right, there's actually, well, 9,999 if you don't include 0, 0, 0, 0. Okay, so maybe 10,000. So this is my codomain, and what you want to notice is that not everything in the codomain is listed here. Okay, and when it comes to codomain, we don't necessarily have to map to everything in the codomain. But let's say, for example, Tom maps to 1, 1, 2, 1, Lisa maps to 1, 3, 4, 7, Terry maps to 2, 3, 4, 1, 5, and Jean maps to 4, 8, 2, 1. This is still a function. This is still a function because what we're doing is we're taking every member of our domain, Tom, Lisa, Terry, and Jean, and we're mapping it into something in our codomain. That's the Y set. And for every one element in the domain, it maps to one and only one element in the codomain. Okay? So we don't have all 10,000 numbers, but we do have enough to allow us to map to every member of our domain to the codomain. Okay? And in addition to that, to make sure that we only have one going to one. One element in the domain going to only one element inside of the codomain. And so this is, again, a functional relationship. Now, we can also do this with, say, for the example, things algebraically. So let's look at one here. Let's say, for example, I take f, and what we'll do is we're actually going to write this out, and the first element here, we're going to call it, it's going to be z, so it's going to be the set of integers, okay? And the position here, that's the position called the domain. And we're going to map this onto all of just what we call z plus. And z plus is all the positive integers. Okay, so we're going to go from z into z plus. All right, and we're going to define this as f of x equals x squared. F of x equals x squared. So in this case, we can take any element in z. Okay, f of -2, and that's going to be -2 squared, which equals 4. Great, that works out really well. Okay, I should actually add to this f of z plus, right, union 0. Okay, I actually should union this with 0 because that way that's going to allow me to take 0, which is in the domain, to 0 as well. So f of 0 we know is going to equal 0. Great, this is good. On the other hand, f of pi is undefined. And the reason why f of pi is undefined is because f of pi is not in the domain. The domain is only the set of integers. Pi is not an integer, so consequently we can't include f of pi, all right, inside of our function, or we can't like actually figure out what it is inside of our function. Now, if we had started out with the real numbers, say for example r into r, then what we would end up with is we actually would end up with some value for pi. We'd end up with pi squared. Right? But because pi is not a member of our domain, we can't actually find a value for f of pi in this case. Right? And that has to do with how we end up defining our domain. It's actually a pretty key difference. Normally when you're working in algebra, it's just going from r into r. But for us, we can do things like we can move from the integers into the integers. We could move from, like for example, a set of Cartesian products into another function, okay? And I'll show you an example that looks like that. We get a lot of flexibility here, and so consequently you want to actually pay attention to what your domain is, okay? And don't make assumptions about what your domain is. And also, we're going to see a little bit later on when we do one-to-one and on-to that you're also going to want to make sure that you pay attention to what your codomain is. So I told you before, and just a moment ago, that we could actually take a function, and let's say, for example, we go from z cross z, so that is z squared, and we want to map onto just into z. That is that we're going to take two values, or two integer values, and we're going to end up mapping them onto a single integer value. So for example, f of, let's say we have f of xy now, is going to equal 3x minus 2y. And so what that would look like is then we take f of 3, negative 1, and that equals 3 times 3 minus 2 times negative 1, and that ends up equaling 11. Or we take f of 4, 2, and that'll look like 3 times 4 minus 2 times 2, which equals 8. Okay? And so in this case, our domain is defined as z cross z, so we could take any set of, any pair, any tuple of integers and map them onto the integers. Now let's take another example. We'll take f of pi and negative 1. Now again, notice that the Cartesian product here is z cross z. So since it's z cross z, what that tells me is that I cannot, in fact, plug in pi. All right? So this is, again, is undefined. It's not a member of our domain. We can't put it in. We can't plug it in. So one of the things that we want to get about domains and codomains, the first thing is that with a domain sets up what possible values that we have that we can plug into a function to get something out. Okay, and that's our domain. Our codomain is going to be the group of all objects that we can actually plug something, pull something in from. So like, for example, when I went in and I said, in this example here, if you remember, I said, oh, I'm going to have to take it z plus union 0. Well, in this case, the reason why I had to do that is because if I didn't have the union 0, then when I plugged in 0, which is in the domain, what I would end up with is nothing that's actually in the codomain, because z plus is only positive integers. So I needed to add in the 0. I needed a union with 0 so that I could get everything out of my domain, so that I could actually find a value for my function from everything inside of the domain. And that's an important piece. Okay, that's going to be an important piece that's going to end up helping us to define what a function really is. And then the second piece here is that we don't actually have to utilize everything in our codomain. Okay, so like for example, in this first case where we picked the set of 4-digit strings from 0 to 10, we actually only mapped to 4 elements in that codomain. The codomain has 10,000 elements. We only mapped to 4 of the elements, and so consequently we didn't have to actually utilize all the codomain. The next concept we want to demonstrate has to do with this idea of a range, and the range is probably something that you're a bit more acquainted with than the codomain. So the range is going to be the subset of the codomain that has at least one element of the domain mapped to it. Not the codomain, but the domain mapped to it. And these are the set of all possible outputs to the function. So if you remember that example that we had Tom, Lisa, Terry, and Jean, and they mapped to individual like identification numbers. Now Tom, Lisa, Terry, and Jean could at most only map to 4, okay, 4 identification numbers, of each one mapped to a different one. Now notice that this is not, in fact, the entirety of the codomain, right? We had 0, 9 with a set of strings from 0 to 9 with a length of 4. And so consequently, what we're going to say is we're going to say, okay, well, the range is this subset, and the range is going to end up being 1, 1, 2, 1, 1, 3, 4, 7, 2, 3, 1, 5, and 4, 8, 2, 1. So it ends up being everything that, in fact, this function maps to. All right, and that's it. That's the range. If, on the other hand, what we wanted to do is we wanted to look at something algebraically, by the way, and let's actually say, okay, I want f going from R into R, so the reals into the reals, and we take 3x minus 1. Now, 3x minus 1, the domain is all the reals, and you'll actually think, okay, so this is a line, looks kind of something like this. Okay, here's the xy axis. This is just a very, very basic rough sketch. It looks something like this, and what you'll notice is that the domain, which is all these values on that y-axis, is going to be all real numbers. So, or excuse me, not the domain, but the range is going to be all real numbers. We can actually get any real number that we want from 3x minus 1. So, in this case, right, our domain is R. Our codomain is also R. And our range turns out to be R as well. So it's all real numbers. Take one more example. Let's take, for example, we take f of x equals x squared. We all know that this is a parabola. And we're going to say that this goes from f, from R into R again, from the reals into the reals. So when we map it, or we create a graph for it, algebraically, we're going to see, there we go, right? We've got that parabola. Now what we want to notice here is that the domain is going to be all real numbers, because that's what we defined it as. The codomain is all real numbers, but the range here in this case is going to only be the set from 0 to positive infinity. So we're not going to be able to get any negative numbers from f of x equals x squared. Okay? And so I just want to point that out, that we can actually have, either we can have the same codomain and range, or we can actually have different ones. And still have our functions be just fine, not a problem at all. All right, so the last question that I want to answer here is whether or not our function is what we call well-defined. And maybe it doesn't make as much sense to talk about it, the function being well-defined, as is the relation well-defined. So what we mean by a function being well-defined really goes towards the definition, right? And so if you remember, the definition says every element, that's the first requirement, is every element in the domain, which we'll call x, maps to 1, and so here's the second requirement, maps to 1 and only one element in the codomain, which is y. If we violate either one of these, what we have is not a well-defined function. So let's actually take a look at some examples to see what this means. So on the one hand, let's take, for example, let's say x is, I've got 1, 2, 3, and y is A, B, C, D, and E. Okay? Now, what I'm going to do is I'm going to have 1 is going to go to A, 2 will go to B, 3 will go to C, and then I'm also going to take 1 onto D, or 2 onto D, and 2 onto E. This arrow diagram shows a not well-defined function. So this is not well-defined. And that's because it's violated the second condition here, right? Maps to 1 and only one element in the codomain of y. Okay? So this is not well-defined. That's the first condition that shows us not well-defined. On the other hand, we can imagine a different arrow diagram that looks like this. I've got 1, 2, 3, and 4. And by some happenstance, I have A, B, and C in my codomain, and 1 goes to A, 2 goes to C, 3 goes to B, and 4 goes to nothing. Okay? So since 4 does not go to anything, does not actually map to anything, this is also not well defined. And that violates the second condition. Or, excuse me, that violates the first condition, every element in the domain X. Because that's an element in the domain X that doesn't map to anything. Okay? So, on the one hand, 2 maps to more than one element in Y. And then we have 4 maps to nothing, is my other one. If we have either one of these things happen, then what we have is a not well-defined function. So arrow diagrams make these things kind of easy to work with. On the other hand, we may actually have to look at some functions and think through them, maybe think through some different possibilities like cases, like when we were doing proofs and definitions. So let's take, for example, let's take f of z, z cross z, okay? And what we're going to do is we're going to say, and we'll map that onto all of z, okay? And then we're going to define this function. We're going to say that f of x equals x plus y divided by 2. So I've got x plus y divided by 2, or excuse me, f of xy equals x plus y divided by 2. Now in certain cases, no problem, right? F of 1 equals 1 plus 1 divided by 2, that equals 1. But let's think through where we might actually run into problems. What if, right, we take f of 1, 2, and that equals 1 plus 2 divided by 2, which equals 3 halves. Now I have a problem. The problem is that my codomain is z. Z is my codomain, and since z is my codomain, 3 halves does not belong to z. So 1, 2 maps to nothing. Maps to nothing in z, and that means the function is not well defined. So you can see we actually have to be really careful about matching up our domain, our codomain, okay, and our function to make sure that we actually preserve that kind of mapping. So let's just kind of review some of the basic things that we went through. It's kind of a quick lesson. One, we have a function, and a function is a relationship between two sets, x and y, where what we have is we have for every element in x, okay, we get one and only one element in y, right? And that's a key distinction. We have that key relationship. X, we call x our inputs, and those are going to be the domain, and our outputs, all of our possible outputs, are going to be called the codomain. The subset of the codomain that gives us all of our actual outputs from the function f is called our range. And those two things can actually be different, and that's actually going to be a really important part. And then finally, we have this old idea of well-defined. A function is well-defined if it follows those two key aspects of the functional definition. One, that for every element in the domain, we actually have an output. There's an actual output. And then two, that what we have is that every input in the domain maps to one and only one output in the codomain. Having those two things for any relation makes it in fact a function, and it makes it what we call well-defined. So this finishes the lecture. We'll be continuing to work on functions. We'll be looking at floor and ceiling functions. We'll be looking also at one-to-one, onto, all sorts of those kind of things. So be on the lookout. We're going to actually start to really dive into functions a bit more later.